What's that P stand for? No. Percentile. So they want the 15th percentile. 15th percentile. Came down, just went around, checked the homework, so you got to get it out. I'll check it here in a minute. We're going over it right now. 15th percentile. If we're looking at the 15th percentile, what percent of the grades, or what percent, not grades necessarily, what percent of the information is to the left then? So we're trying to find that number right there, right? And it said use table, but we're not going to. Get out your calculator soon, because I'm not walking back there and getting mine.
What page are you on?
Am I on the wrong page?
I'm a little confused over that.
Yeah, my fault.
It's all right.
I turned back too far. I turned back to the previous assignment. Thank you for telling me. Let's see here. In exercise 910, graph population distribution is shown with its mean, standard deviation, so on, so on, so on. So we're looking at number 9, and it's got a graph that looks like this. Is that graph normal? No. But what we're saying is we can take all the means, find a bunch of little samples. So we find a sample, 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 sample. We can take the means of each of those samples, and when we take the mean of each one of those, they're all basically going to come out to be the mean of the entire population. And then it would, so all those means would make a normal curve. Here they want us to, it says the sample size is 100, so n equals 100. Decide which of the graphs labeled would most closely resemble the sampling distribution of the sample means for the graph. Explain your reasoning. They tell us on number 9 that mu is 16.5, is that right? Somebody help me out, what's sigma, the standard deviation? 11.9. So we're looking at the graphs that they got at the bottom there. If we take all of this and it's take all these samples and it's going to turn it into normal, they want to know which of those 3 graphs, A, B, or C, is this going to be. So we look at it. First thing I would look at, mu 16.5. Any of those graphs down there have their mean is 16.5? All of them do? So that doesn't help us very much, does it? So we know right here in the middle should be 16.5. One of them we can get rid of right away. Which one can we get rid of? B. Because we know if we do this, it's going to approximate it to the normal curve, not that other curve. So it's going to be one of those other two. We have 16.5 and it's 11.9 is our standard deviation. So that means each time we're going up by about 12. So this would be about 18.5, 30, and 42. Any of that stuff on there anywhere you see? Any of the graphs have numbers like that somewhere close? C makes it real narrow, right? Is it going to be spread out this much by 11 each time? If it's that narrow, that's probably going to be something like 0.11 or something. So which one do you think it is? A. This. Oh, I'm sorry. It's not A. Because we messed up here. This is the standard deviation of this. What do we need to do to that? We got to change it to that, right? Does anybody remember how to do that? Sigma over square root of n. What is sigma again? 11.9, what was in? Divide by 10, or square root of 100, but divide by 10. Somebody do that for me. 1.19. Now when I look at my graph, is it going to go up by 12 each time? No, now it's going to go up by a smaller amount. It's going to have 16.5 in the middle, and it's only going to go up by 1. So that'd be like 16.5, 17.5, 18.5, 19.5. Now which graph looks closer? Now let's see. My fault. Forgot what I was doing. Other questions?
Five through eight real quick.
Determine whether the statement is true or false. If it is false, rewrite it as true. Number 5, as a size of a sample increases, the mean of the distribution of the samples increases. As the size goes up, does the mean change? No. What does change? The size of the sample. All right. What happens to the standard error as the size of the samples go up? It goes down. So that one was false. Number 6. As the size of the sample increases, the standard deviation of the distribution of the sample means does what? Or it says increases. So what happens here when we make this bigger and bigger and bigger? Let's try it and see. This was 100. Let's say our sample size was 1,000. Somebody do that on their calculator for me real quick. 0.3763. What happened is we made the sample size bigger. The standard error got smaller, so we should change that last word to decreases. Number 7, a sampling distribution is normal only if the population is normal. Can we only change this to be normal if the original population is normal? No. We can also change it to be normal if our sample size is what? Other one. Other one. Greater than or equal to 30. So if n is greater than or equal to 30, then the sampling means are also going to be normal. If the sample size is at least 30, you can use z-scores to determine the probability that a sample mean falls in a given interval of the sampling distribution. True or false? True. That one's true. All the other 3 were false. That one's true. We just got done saying that on the previous problem. Other questions?
13.
The population mean, standard deviation are given. Find the required probability and determine whether the given sample mean would be considered unusual. If convenient, use technology. So have your calculators out so you can do this for me. 13. Says for sample size n equals 64, so that's one thing. Notice every time, I'm not writing this down just so you can see it because you got a book there. I'm writing it down because this is the information I need to be able to plug in stuff to the calculator. And this is what you should do. Find the probability of sample mean being less than 24.3. So we want the probability that the sample mean is less than 24.3. That's what we're looking for, is that probability. And it tells us that mu is 24, standard deviation is 1.25. First thing we got to do, and these are all these problems for this section, first thing we got to do is what I didn't do on the other one and messed it up, is we got to find We don't have to find mu. We have to find the mu of the sample means, and we gotta find the standard error, or the standard deviation of the sample means. What do we know about mu of the sample means? Boy, if you can't find this on the test next week, you're gonna miss some easy points. It's the same thing. So if this is 24, what's this? 24. The standard error of the sample means, we do what we did a second ago. We take 1.25 and we divide it by what? Square root of n, which is 64. Somebody do that for me.
16.
Say it one more time.
0.16.
What should happen to the standard error? How should it relate to the standard deviation of the population? Should get what? Should get smaller, because what we're doing is we're compressing this in, and it's going to be a steeper graph. Now, probably ought to make you do this on the chart since everybody seems so alive today, but we'll punch it into the calculator. What 4 things do we need to be able to punch into the calculator to find this, the area, the probability? What do you put in first? Your low limit, then what? High limit, then what? That mu, then what? Standard error. All right, so we're going to punch in those 4 things into our calculator. What do we hit first on our calculator? Second bars. I'm hoping you have all this written down somewhere. Normal CDF. We're going to actually use this same setup today. Second bars, normal CDF. This time, what's our low limit? Look at what we're doing here. We're trying to find all of the chances, or all of the probability that it's less than 24.3. So how low are we going down? Negative 10,000. How high are we going up to? 24.3. What's our mu for our sample means? What's our standard error? 0.16. Plug all that in, hit enter. 0.969. I don't know, that seems awful high, doesn't it? Does that seem high? About 97%? So what are we saying here? We're saying that 97% of the data falls where?
Between negative 10,000 and 124.3.
So let's, boy, that just doesn't seem right. So let's graph this. If I graph this, that's our normal curve, right? And this is what you got to be able to do. I don't want you to come in here and be able to stick stuff into your calculator. I could train a monkey to stick something into the calculator and do it. All right? Understand what it means. This problem, they didn't give us what it was or anything. Let's say 24.3 is the average speed limit on Oxford, or the average speed of a car on Oxford Gettysburg Road. All right? So we're saying if we go out there and we stand out there and we test every car that goes by, that 97% are going to be at 24.3 or less. Now, I know this doesn't make sense as far as Oxford Gettysburg Road goes. Just bear with me on that because I couldn't think of anything else. Does it make sense if the average speed of all the population is 24 and the standard deviation is 1.25? Does it make sense for 97% to be at 24.3 or lower? I don't know. Let's find out. So if I graph this, 24.3, we want to put what there? What goes in the middle? 24. I don't know why I started to put 24.3. And we're gonna use this, 0.16. 0.16 is our standard error, so we're gonna go up by 0.16. So I'm gonna use 0.2 instead, just to make it easier, so I don't have to write out so much. 24.2, 24.4, 24.6. Do I need to go out any farther than those three standard errors? No, that's about as far as you go, right? Because anything out past that is very unlikely. If I go down this way, 23.8, 23.6, 23.4. We're at 24.3. 24.3 would be right about in here. Does it make sense for that to be 97% of the data? Yeah. All right? But you got to be able to understand, number one, does my graph look correct?
Yeah. Ish.
Should I have all this extra area out here? Because I can tell Lucas is going, well, that looks like more than 7% of the data out there. And he's probably right, because my graph should have looked more like that, probably, right? It should have been more straight up and down where we have that, because we're not spreading it out very far. If I did that and I put that right there, now would it look more like that's 97% of the data? All right? But you need to be able to understand what you're looking at here. And what you're looking at is you're saying, if I take a whole bunch of samples, if I go out there, if Lucas goes out there and he stands there and he guns 15 cars and takes their speed limit, then Sydney goes out there and she does it, then Katie goes out there and she does it, and we take all of those samples and we average them up, what percentage of them are going to be at or below, the average is going to be at or below 24.3, and we're saying about 97%. Other questions? Everybody will be able to do that next week. Right, Dalton? Dalton's got it under control.
Do it.
18 fly eggs. The numbers of eggs female houseflies lay during their lifetime are normally distributed with a mean of 800 eggs. So the mean of the population is 800. We're saying that each housefly normally lays about 800 eggs. Standard deviation of 100 eggs. So our sigma, standard deviation of the population, is 100. So that's saying, let's graph this real quick, and I'll try to draw my graphs a little better. If I graph this, what goes right there in the middle? 800. And they said this is normally distributed, so it's going to fit the curve. What's going to be that next number right there for the first standard deviation? 900. How about for the next one? 1,000. Next one? 1,100. Here? 700. Here? 600. Third standard deviation to the left? 500. So that's what the curve looks like if we were doing the whole population. Let's see, what else do they tell us here? Random samples of size 15 are drawn. What a job to have. You go out and you catch 15 house flies, and you do it over and over and over again, and you see how many eggs each of those house flies lays. Is that going to be your job, Sophie, at some point in your life? And catching flies.
How you catch a fly without killing it? Job. Fish net. Very small fish.
So we got this. What's the first thing we gotta find so that we can look at this, the sample means? Every time, first thing we gotta find, the mu of the sample means and the standard error, or standard deviation of the sample means. What's this? 800, that stays the same. You can't get that right on the test next week. I'll probably shed a tear for you. How do we find the standard, or the sample standard deviation?
Square root of 15.
100 divided by the square root of 15.
25.8.
Say it again.
25.8.
25.8. Now watch what happens. This is where I usually don't draw the graph like I should. What number is going to go in the middle? 800. When I draw this graph for these sample means, I should draw the exact same numbers on the graph as I have right here and show it from that. All right, and that's what I'm going to do this time. So it's 800, 900, 1,000, 1,100, 700, just to try to make sure you understand this as well as you possibly can. 500. So that graph should look the same. When I go to make this new normal curve, I'm going to use the 800 as my mean and 25.8 as my standard deviation. We're going to round that off to just 25 to make it easier. We're going to use the 25.8 when we do the calculations, but for my graph, to make it easier on me, we're just going to use 25. So I go 800, that's going to be right in the middle. What's going to be one standard deviation above that? 825, that's going to be somewhere about right in there, right? What's going to be one more? 850, and what's going to be the third one? 875, that should be getting real close down here to the graph on our curve, right? When you get out to the third standard deviation. What's going to be one standard deviation below that? 775, 750, and 725 is going to be somewhere about in there. So our graph should actually look, I got off a little bit because I'm standing here sideways. Our new graph is going to actually look something like that. What did we do to the data? We sort of squeezed it all in. All right? So that's what our new graph should look like if we put it right on top of that one. What did it say to do? Number of eggs, standard deviation, sample size, and what were we trying to do here? And sketch it. So sketch the graph, find the mean. So we did everything that they didn't ask us to find the probability. They just said draw the graph. It's going to look something like that. Find the mean of the samples and find the standard error of the samples. So those right there are our answers. What if they did say, because I don't feel like doing it anymore, what if they did say find the probability of something? Brendan goes out and he catches this one fly and he thinks it's a special fly. Oh my God, this might be the super fly of all time. And that fly, what might a superfly? Let's make up some number for a superfly. How many eggs might a superfly lay? 800. 800? 801?
It's a superfly, probably don't lay that.
Superfly don't
Yeah,
lay
but
eggs.
it probably don't lay birds.
So it just gives birth.
No, they don't even.
So he finds this. Now we can't just say one superfly. It's got to be a race of superflies if we're doing this, right? Because we're finding the sample means. So he finds these flies, and they just magically, they don't lay eggs. They magically duplicate whatever. He comes back an hour later after eating lunch, and
15.
there's 30 flies in there instead of 3. And what in the world's going on here? So he's trying to count the eggs. Let's say there are no eggs.
Got it.
So we want the probability that our X bar is, let's say, less than 1. All right? Because there are no eggs in there. Less than 1 would be 0, right? So we want that probability. What are we going to put into the calculator?
Negative 10,000.
Negative 10,000, that's our low limit. 1. 800. 25.8. Somebody punch that into your calculator, see what you get.
0.
Sorry, Brendan. What's the chance of Brendan coming up with this race of superflies? There ain't happening.
It's slim.
No, it's not slim.
No.
That's not slim.
What do you mean? It could happen.
Apparently not.
It says so. It's all conspiracy theory.
All right, Brandon.
Brandon who? Oh.
I knew he'd get it at some point.
He told me.
All right, well, we're going to cover today normal approximation to binomial distributions. Anybody remember what a binomial was from last chapter?
Something to do with
2. It's when you have 2 possible solutions or 2 answers. Normally, remember we had to change it into a binomial. So we changed it into something like, if I was talking about your guys' ages, I wouldn't want to go completely by your ages. I just want to ask you a question like, are you 17? And then you could switch your answers to yes or no. Then I have a binomial. So we're going to try to change those into binomial distributions. A lot of the stuff that we do will be the same as what we did on the other sections in this chapter. But the one thing I'm going to say right now when we're doing binomial, and the one thing you're going to have to change, and I'm just going to put this up here right now. This is my little normal looking binomial. It's a binomial. It's normally distributed. The bad thing is with this, if we try to use the normal CDF, then we miss a bunch of this area because the curve looks like this. Let's see how well I can draw this curve. The curve looks like that. Well, if I'm trying to find the area from, let's say, right there down, what's happening with this part? I'm missing it, right? I'm not getting all the area. Because when we switch this up to be, at the start of this chapter, or actually at the start of the last chapter, we talked about discrete. Anybody remember the other word? Continuous. Discrete and continuous. A binomial distribution is discrete. It goes numbers. 1, 2, 3, 4, 5, 6, 7, 8. If I ask you guys your ages, and I say, is your age 17? We're not going to come up with any 3.5s, right? It's going to be 5 of you answered this, 6 of you answered this, 7 of you answered this. So it's going to be a whole number. That's discrete. What we've been doing has been continuous. We just got done with something that said 24.3. That's continuous because it's going 24.3, 24.3, or yeah, 0.31, 24.32. So it's continuous. Well, if we're using a binomial, we're missing, if we're switching this from a binomial into a continuous, we're missing some of this stuff right here, some of this area. So we're not getting all the total probability. Well, what we need to do with that is fix that as we go. And what happens is, if you look at that part right there, Well, we also got some extra right here. What do you think's approximately true about those spaces? They're about the same, and we can change it just a little bit so that it actually fits it a little better. And that's what we're going to do in this section. So we're going to change it to a binomial. Hopefully you remember some of the stuff with binomials. If not, we're going to go back over some of it anyway. Hopefully that'll jog your memory. For binomials, you need to know all these things for binomials. Need to know. So when I'm doing a binomial, the first thing I do is I write down N, P, and Q. Anybody remember that? Can you remember that? Writing down N, P, and Q in the past?
N means number.
N means the number of trials, number in your sample, whatever. What's P mean? Little p. Probability. And what's, then put Q up here. Well, I do have Q right here. What's Q mean?
Towards left.
Towards left.
P means probability. Q is 1 minus the probability. All right? Q is the complement of the probability. Might have to go out and buy a pack of new green pens this weekend to grade these tests next week.
Why not red?
I don't use red. Why not pay attention to what I've used on your test in the past and see
No, I just look at the number.
that number's written in a certain color? What is that color?
It's white in the first book.
I sorted it. Why am I still having this discussion? Probably is.
You gave some.
Normal approximation of a binomial. Move that out of the way. Normal distribution is used to approximate binomial. I wouldn't write all this down. When it would be impractical to use a binomial distribution. If you remember last chapter, some of the problems that we did said like a doctor does 100 surgeries. What's the probability that 86 of them are a success? Well, that means that we'd have to go well, actually we'd have to start where? 0, 2, 3, 4, 5, 6, 7, 8. And if we want the probability that 86 are successes, what number do we have to go up to? 86. And we'd have to find the bar, the area of that bar, 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 so on, so on, so on. And what would we do with all those areas? Add them all up. Do we really want to go out 86 times and find 86 different probabilities? No, that's why we're trying to approximate this to that normal distribution. All right, because we don't want to go out that far. We want to be able to just use our calculator and say, all right, what's the probability that it's 86 or less are successful? Or hopefully, we probably wouldn't even go that way. Hopefully, if we're doing it with a doctor, we want to say what? That we want the probability that it's more than 86, right? Hopefully, we want more successes than failures. This I would write down. Normal approximation to a binomial distribution. This is important right here. This is the first thing you got to check. You got to check and see if we can approximate this. If not, then we just can't do it. So you take n times p has to be greater than or equal to 5. N times q has to be greater than or equal to 5. If either one of those is not true, then we can't approximate it using the normal curve. So that's the first thing you gotta check. You're gonna take n times p, n times q, and see if it's 5 or more. If it's not, then you stop right there and you say this can't be done using a normal approximation or using a binomial distribution. If it does work, if both of these, when you do that multiplication, if both of them are larger than 5, then we'll continue on and try to normally approximate the situation, whatever it is. Before you can do this, what things are you going to have to find? N, P, and Q. You got to find those three things. The mean, remember the mean, we did this for binomials last chapter. This was the easy stuff that when we took the test last chapter, everybody missed, and it just drove me nuts because this was what was supposed to have been easy on that chapter 4 test. Mean is n times p. Does anybody remember what's the sigma? The standard deviation. N times p times q.
Squared.
Not squared.
Root.
Square root of it. Standard deviation, the sigma, n times p times q, you take the square root of it. So to find the mean, this is for binomials. Same as we learned last chapter. Find the mean and standard deviation of binomial, that's all you have to do. The thing that bothered me so much last chapter was everybody forgot how to do this. The harder stuff, we had to make that big long chart. And you remembered how to do that, but you didn't remember how to do the easy thing where it was just take n times p to get the mean and standard deviation. So if it's a binomial, if we can use the binomial setup, then that's all we have to do. N, again, is the number of independent trials. P is the probability of a success on each trial. And Q is the complement of that, or 1 minus that. So what all this is showing, the larger our sample sizes get, what happens to our graph each time? It gets closer and closer to what? The normal curve. Gets closer and closer to being normal. Notice this one. Does it really look real normal? Not really. We only did, it looks like we only had a sample size of 4. Then we had a sample size of 10. Does that look sort of normal? Yeah, it's not too bad. That's a sample size of 10. Then we got a sample size of 25. Does that look normal? Yeah. Then we get a sample size of 50. That one really looks normal, right? It looks like the normal curve would fit right on there. So the bigger your sample size, the better it's going to fit the normal curve. And the more precise we're going to be able to be with our calculations. Decide whether you can use normal distribution to approximate X, the number of people who reply yes. If you can, find the mean and standard deviation. So this first one says 62% of adults in the U.S. have an HD TV. That's probably a higher number now. Our book's sort of old because now if you don't have HD TV, what happens? You don't get channels. They don't even come in on the SD TVs anymore. You randomly select 45 adults in the U.S. and ask them if they have HD TV in their homes. 3 things we need to find. We need to find N, we need to find P, we need to find Q. What's N this time? 45. Have your calculators out so you can help me here in a second. What's P? 62%. What am I going to change that to? 0.62. How do I find Q?
24.
Say it again.
38.
0.38, subtract that from 1, right? Now, the first thing we're going to do to check to see if we can use this binomial distribution setup is we're going to take n times p and n times q. So we're going to take 45 times 0.62
47.
and 45 times 0.38. And all you really got to do with those, we don't have to do anything with them. We just have to look at the answer. When you multiply 45.62, is it bigger than 5?
Yes.
Yes. So that one works. We take 45 times 0.38, is it bigger than 5?
Yes.
So if that works, now can we go ahead and use the binomial setup? Yeah. And what we're saying by using the binomial setup is then we can find the mean just by doing n times p. We can find the standard deviation by doing the square root of n times p times q. Well, we already did n times p if you were doing it there on your calculator. It was right here. What was n times p?
27.9.
Say it again.
27.9.
So that's our mean. What's our standard deviation? N times p times q. And let's take the square root of that.
$3.25.
3.25. We'll say 3.3. Anybody else get that?
Yeah.
Those are the two answers that they wanted this time. Now, if we wanted to go a little farther, if I wanted to draw the graph, our graph's going to have 27.9 right in the middle. How much are we going to go up or down by each time? 3.3. So it's going to go like 31.2, 34.5, 37.8, and then go down 3 spaces this way, and our graph's going to look something like that. Now remember, our graph looks like that, but it was actually, since it's binomial, it would actually be something more like that. It would have the bars, but we're going to approximate it to be normal. They didn't ask us to do all that, but you need to realize that for what we'll do here in a minute. On this one, that's all they ask us to do. They ask us to tell, can you use the binomial setup? Yes. What's the mean and standard deviation if we use it? 27.9 and 3.3. Is that what we got? Looks like it. Next one, 12% of adults in the U.S. Who do not have HDTV in their homes are planning on purchasing one in the next 2 years. You randomly select 30 adults in the U.S. who do not have it and ask them if they are planning on purchasing one in the next 2 years. We want to know, will this fit? Well, again, the first things we need to find N, P, and Q. What's N this time? 30. What's P this time? 0.12. What's Q this time? 0.88. N times P, 30 times 0.12. What's 30 times 0.12? 3.6. What's that tell us?
Right.
Can't do it. Is that bigger than 5?
No.
So if that's not bigger than 5, can we set this up using the binomial setup? No. So we just put can't use binomial. We can't use the binomial setup on this because that didn't come out to be larger than 0.5 or larger than 5. So you can't use the binomial setup. not even sure why I did this. I did N times P, N times Q. Did I even need to do N times Q?
No.
Sort of silly to do because we already know it won't work. Binomial distribution is discrete and represented by the probability in the histogram. That's what we talked about earlier. So when we were doing the binomial stuff, we were finding the area of each bar and adding them up. To calculate exact binomial probabilities, the binomial formula is used for each value, and we add them all up. Geometrically, this corresponds to the areas in the bars. The bad thing is when we're trying to approximate it to the normal curve, are those bars completely filling up that normal curve?
Yes. No.
Not quite, right? Now, so we're going to do something, we're going to have to do something, and that's what this is, the correction for continuity. We're going to correct for that mess up. We're going to correct for these little points that stick outside and these little empty spaces. We're going to correct for that so that we can find a better approximation of the area. Does that make sense? Brenda, that makes sense? When you use a continuous normal distribution, approximate binomial, write this down. This is important, so write this down. I'll give you a minute. It's like 2 sentences. Man.
I just asked a question.
The whole thing, yes, I'm sorry, you're right. You just asked a question, I shouldn't have been mean about it. Yes, please, the whole thing. Make this so it fits that normal curve a little better is we're going to move our low limit, whatever our low limit is, and our high limit out a half of a unit. So now instead of using that midpoint, let's say that midpoint right there was 10, instead of just trying to put 10 in there, because that's a real little small thing, we want the whole bar. We're going to go down to 9.5 and up to 10.5 to account for that bar. So that's all we're going to do. So on our low limit, we're going to go down an extra half. On our high limit, we're going to go up an extra half. Now some of them won't have a low limit and a high limit because we've had the negative 10,000 and the positive 10,000 if we're just going all one direction, right? So if we were just trying to find from here down, which one of those two do we need, not need to do? Do we need the 9.5 there? We're considering that in there anyway, right? So we just go up to 10.5, that would be our high limit, and our low limit would still be negative 10,000. What if we were going this way? What if we wanted to go from here over that way?
Negative 10,000.
If that number right there was 10, 9.5, and we would go from there up to positive 10,000. So you got to know which way you're going. Sometimes you want to do both. Sometimes you want to do both because I just want to be right here. I want to know exactly 10, then I go 9.5 to 10.5. Use a continuity correction to convert the binomial interval into a normal distribution interval. The probability of getting between 270 and 310. So if we want to, our probability is between 270 and 310. This is the low limit, that's the high limit. What am I going to change that 270 into? If it helps you, we're going 270, 310. Draw a little something here. We want that part of the curve right there. Well, what am I going to do 270 if that's my low limit? Change it to
265.
269.5. What am I gonna change the 310 to? 310.5. So I'm gonna go out just a little farther on each one of those, and it's gonna be that area. So we go our probability is gonna be from 269.5 to 310.5. So that's what you're gonna do, just to change it so that you can plug that into your calculator. We get at least. So we're saying the probability, we're at 158. We want at least. Which way am I going? Up or down? If we want at least 158. Up. So what's my probability going to look like? Probability of what? X is greater than. Do we put in 158? 158 and a half, so we go over here. What do we do if we want to go from 158?
Oh, so 157.
We go 157.5, because we actually want to start down here so that we include all of that. So we want X to be greater than 157.5 so that we get that entire bar there instead of skipping part of the bar. Mike, will that make any sense? You can handle that, you think? Probability of getting fewer than 63. So we're at 63, what's getting fewer than 63 mean?
63 or 62.
Fewer than 63, do we want to include 63? No, so where would we start at? 62.5 and down. We want to go from 62.5 and down. So you got to read the problem carefully and make sure you understand what you're getting. So we're at 60, 61, 62, 59, 58. We want all those. So we want X to be less than 62.5. And all we're doing with each one of these is changing it so that we get the entire graph and not miss part of it using this binomial stuff. I'm going to put these up here. You can write these down. Might just want to write down this part over here. First thing you're going to do, find NP and Q. Number 2, decide whether we can use the binomial setup or not. And that means n times p's got to be greater than or equal to 5, n times q's got to be greater than or equal to 5. If it works, if yes, then we do this. We find the mean and the standard deviation. Mr. Leonard, any of this sinking in? Apparently not.
You looked at you. He's not like you.
Hey, what?
He is not like you.
Breaks my heart.
Enough for today.
That's enough?
Yeah.
Too bad.
I'm talking about all day. Okay.
After 8:52, I don't care what you are.
I don't even care. Don't be here.
I think I've just learned too much today. It's enough.
You already knew most of
You're supposed to have done most of it. Two more steps on that. Do your correction, your continuity correction. So you add or subtract 0.5 from the endpoints, and you got to be able to figure that out on your own. Actually, there's 3 more steps. These 2 steps, do we really want to go through and find each z-score and do it all that way and use the chart? Probably not. What are we going to use? Use your calculator. On your calculator, you're going to punch it into the normal CDF just like we've been doing. So you're punching it into the normal CDF. And we'll do a problem here in a second, and I'll show you how to do it. Now, does that mean that I don't want you to remember how to do these z-scores? You think you're going to have to find the z-score on the test next week? Probably so. Remember, z-scores, just you take the score that you're looking at minus the mean of the set divided by the standard deviation. Easy stuff, right, Sophie? Let some of your vast knowledge seep over here to Mr. Leonard, since apparently he's looking at me like none of it's sinking in. I must be talking to the wrong ear. Let's go into the stuff goes in the right ear. Is that what it is? Nothing goes in the left. It's a one-way circuit. He's mad at me because he's my aide, and I started making him do his homework in here.
That's what I would have done.
That's what I told him. Instead of sitting in here with that blank look on his face while I'm teaching geometry.
Wait, how many eights you got?
One.
I thought you kicked that one out.
I'm getting ready to kick one out. That might have been brought up last class, wasn't it?
Yeah.
About me firing my aide.
Step it up.
No, you didn't hear the whole conversation. I fired somebody, I don't know, when, 2 years ago?
Hey, fired, huh?
Yep, I went down to the counselor and I said, get him out. So they're no longer my aide.
Why?
Because they weren't doing anything.
Sitting there.
Yeah. They weren't, I didn't have them in class. I had, Mr. A had them. And they were failing his class. I said, come in here and do your math work then. If you're not going to do any work for me, do your math work. Refused to do that, and I said, get him out. I don't want no part of this person. I said, well, you can't just, they got to have somewhere to go. I don't care where they go. I didn't, just like you, did I sign up to let you in here? No. Same thing with us. I didn't sign up to have them as my aide in the first place. Why did you stick them with me? Maybe you should have came and asked me.
Dan's a math teacher. Unless they're gonna help.
Unless they're gonna help do something, I don't want them in here. I'm giving them a free time just to sit here. Didn't make the young lady very happy because she had to actually take a class then after that. 62% of U.S. adults have HD TV in their homes. We did this. but we're actually going to find the probability now. If you want to write down a sample so you know how to do it, especially for a test next week, this might be a good one. You randomly select 45 adults. So right away, what do I know about N? It's 45. 62%, what is that? So what do I write down? 0.62. We can find Q right away also. What is Q? 0.38. Take 1 minus that 0.62. The first thing we got to do is make sure that this fits a binomial distribution. Make sure that we can do that. Now, I think we already did that, didn't we? 45 times 62 was,
27.9.
no, that was the other one.
27.9.
37.9. 45 times 0.38 is,
17.1.
so is both those larger than 5? So both larger than 5, so yes, fits the binomial distribution. The next thing we're going to do is actually find the mean and the standard deviation. Remember, mean is N times P,
27.9.
37.9,
20.
27. 27.9, and Q, or I'm sorry, sigma is N times P times Q,
3.25.
square root, 3.35.
2. See, I worked out about that.
Now we want to find the probability that fewer than 20. So we want probability fewer than 20. How am I going to write that? Fewer than 20.
Less than 1.
Less than 20. The bad thing is that won't work. So let's think about our graph here. We're at 20. We want fewer than 20. So we're going down this direction.
So less than or equal to 19.5.
We got to change that 20 into what? 19.5. So we're going to do the probability that x is less than or equal to, or you can just put less than, doesn't really matter, 19.5. We got to do that continuity conversion. So we want less than or equal to 19.5, because we said we want fewer than 20. Well, give me a number that's fewer than 20.
19.9.
So on, so on, so on. Is 20 fewer than 20? No, so we don't want to take from here down. We want a little farther over here down. So we got to correct for that. In your calculator, what are you going to punch into your calculator? Same as 2 or 3 other sections this chapter.
Second bars.
All right, what numbers? Give me the list.
-10.
Negative 10,000 because we're going down, right? That's our low limit. What's our high limit?
27. Yeah, 27.5.
19.5. That's our high limit. What's our mean? 27.9. What's our standard deviation? 3.3.
0.0054.
Say it one more time.
0055.
0055.
Yeah.
Anybody else get that? So what's our probability that we pick these people? What's the probability, and we get a number that's fewer than 20 that say yes? Less than 1%. So what's that tell us?
Not very good.
Very unlikely. Very unlikely that we're going to get a group of 45 people, and out of that 45, 20, fewer than 20 of them are going to say yes. See if we did all that right. That's what we got for the mean standard deviation. This is what our graph would look like if I wanted to graph it. I didn't graph it. Notice down here, that's our area. Does that look like it's going to be very unlikely? Yeah, it's a pretty small area, right? We do all this. Here I changed it into z-scores and looked at the z-scores. And I got 0.0049. Is that pretty close to what we had using our calculator? Yeah, about 0.5% either way. probably don't wanna change all these into Z-scores every time. In the past, you guys are lucky, because in the past, I made them all change it into Z-scores. Now, I'm just tired of fighting with Sydney over there and just saying, use your calculator. I don't care. This is what you punch in on your calculator. First, you gotta find the mean and the standard deviation and do the continuity correction. Then these are the steps for the calculator. Remember, this is if you're trying to change it into, or to fit, the binomial distribution. This is if you're making it fit the binomial distribution. What's it mean to be a binomial distribution again? Two answers, two outcomes. A lot of times, yes or no. I didn't put all the commas in here. Do I need to put in a 4.5 and say put a comma, then a comma, then a comma? You guys can figure that out, right? I need to do all that? Malachi, I need to do all that? Is that why you're saying yes? Yes, I need to do it, or yes, you can understand to do it on your own? That's what I thought. Ah, there you go.
I can't fall asleep in class, but I'm on medicine and it makes me super tired.
Oh, buddy, can't
I yelled in one of my geometry classes the other day, and it was hilarious because I came over here and I sat down and I yelled so I could watch. I swear it was like all of them. It was like a movie or something, because every single one of them went like this. They all went up at the same time.
I can't sleep in
I couldn't.
class.
What'd you yell?
I just yelled.
What? Like,
I just yelled because they were like, oh,
Scream. Well, you always used to have like the lights on geometry, so I always fall asleep too.
yeah, I don't turn them out anymore because it breaks that thing. Stupid sensor. Every time you punch that, they've had to fix mine like 2 or 3 times now.
This year?
Not this year, because I quit turning it off.
You should turn it off.
No, because last time I did it, I couldn't, the lights wouldn't come back on.
That's okay.
So I had to wait for them to fix it.
Okay with that.
That's your assignment.
You get 2 days.
Again,
You get a week.
I'll see you for a while. I'm gonna put grades in today.
Like next one.
Probably. Put grades in today. Starting off, don't get too excited or too low, depending on your grade, because all there is homework grades in there. Big grade's gonna come next week when we take this test. But I say that, do you really want another 0 to add on top of zeros that you might already have? Probably not. I don't see you till next Wednesday. So that's like 5 days away.
Maybe Thursday.
Probably forget my name in between now and